All right, we're going to look at using all of these theorems in calculus problems. So a lot of times problems will have a couple of these together, or there'll be other parts of the question. Like if you have a 4-part question, 1 or 2 of the parts might be one of these existence theorems. So first, let's just remember what the theorems say. The intermediate value theorem. So this one says, if f of x is continuous on the closed interval a to b, and there is a value of k between f of a and f of b, then there exists at least one value of c on the open interval a to b such that f of c equals k. So remember, graphically sometimes that'll kind of clear it up. We've got your interval a to b, and then f of a happens to be the y value at that a value, and then f of b, so maybe we have this other point up here, right? Maybe this is our function. We'll call this f of b. We're saying that if it's continuous over this interval, there has to be some c on the interval, or in between a and b, such that k is in between the y value. So we're saying there's an x value on the interval where there's a y value between those y values of the endpoints of the interval. So that's our intermediate value theorem. The extreme value theorem is saying that if f of x is continuous on the closed interval a to b, then f of x has an absolute maximum and an absolute minimum value at one of 3 places: at one endpoint, or at the other endpoint, or any other value x on the open interval. So any other x on the open interval, I should say on the interval a to b, such that f prime of x equals 0, or f prime of x is undefined, because those are our possible relative extrema. So we're kind of saying that we've got this interval from a to b, and maybe the graph looks like this. Let's say it's a, we've got a b, and then we've got a graph that looks like this. Right? So we're going to say that there's a relative extrema here at c, and there's also a relative extrema here at d. So we can say, like, on this interval a to b, the closed interval, that this is an absolute maximum. And then for our absolute minimums, we've got one here, and we also have one there. And this is a relative maximum, but it's not an absolute. And the theorem just talks about absolutes, so we wouldn't include that one there. But I do like to point it out. This is our absolute maximum because it's higher than our relative maximum. Rolle's theorem says if f of x is continuous on the closed interval a to b and also differentiable on the open interval a to b, and the endpoints have the same height or same y value, making that means if they have the same height, if I draw the secant line through those, it has an average rate of change of 0, right? So if the heights are the same, then there is at least one value of c on that open interval a to b, so we don't consider the endpoints, such that the instantaneous rate of change, or the derivative at c, equals 0. So a graphical picture of this might be, we've got our interval a to b, we've got our y values are the same height, so again, if I draw my secant line there, since they're the same height, I know the slope of that secant line is 0, or the average rate of change over the interval is 0. So now if I have a graph that looks like this, I know at least once somewhere on there the instantaneous rate of change, like at this c value, right, has to have a slope of 0. The derivative has to be equal to 0. And it actually occurs at another value, so we'll say here's a second place where it occurs, and here's a third place where it occurs. So in this picture I drew, it actually occurs 3 times. Rolle's theorem guarantees there's at least one. Our mean value theorem is a more general version of the Rolle's theorem. So we're going to say if f of x is continuous on the closed interval a to b and differentiable on the open interval a to b, then there is at least one value of c on the open interval, so we're not considering the endpoints, such that the instantaneous rate of change, or the slope of the tangent line f prime of c at that value c, is equal to the slope of the secant line of the endpoints, which is the average rate of change. So this is a less specific version of Rolle's theorem because we don't need this other condition. They don't have to be the same height on the endpoints. So therefore, I'm not going to be able to say that the derivative is 0. I'll just say the derivative is going to be equal to whatever the slope of the tangent line is going to be equal to the slope of the secant line of the endpoints. So here's our picture version of this. So maybe we've got an A and a B, and maybe it looks like this. Right, so our average rate of change is the slope of our secant line. At some point in this interval, let's say it's like right here, some c value on the interval, the slope of the tangent line will be equal to the slope of the secant line. So the instantaneous rate of change will be equal to the average rate of change. All right, so let's look at how we use these in some problems. All right, so first we're going to use this table of value to estimate r prime. Now notice we don't have r prime on the table. This was something that we were struggling with when we had this quiz and test. So we're given r, and they're asking us to estimate r prime of 5, which is not on the table. So R5 would fall between 3 and 6. So an estimate of the derivative would be, let's do the slope of the secant line, and that'll be an estimate of the tangent line at 5. So if I take these 2 points, one on either side of 5, and do the slope of the secant line. So we're going to say a good estimation of the slope of the tangent line will be doing the slope of the secant line. So r of 3 minus r of 6 all over 3 minus 6. So that's going to be equal to 10.4 minus 10.8 over negative 3, which is about 0.133. Explain what this value means about r of t. So we know that the derivative is positive, so that means that r is increasing. So we're going to say since r prime of 5 is positive, then we're going to state what this thing means. The rate, because r is the rate at which something's happening. So the rate at which water is flowing out of the pipe is increasing at t equals 5 hours. This one's a little tricky because they're talking about a rate. First of all, like r is a rate, so now r prime represents the rate of a rate, which is sort of interesting. So just make sure you use their language right back at them. Like r is the rate, right, measured every 3 hours. So this function r is a rate. So I'm just going to say since the derivative of that rate is positive, then the rate is going to be increasing, because we know when the derivative is positive, then the original is increasing. And they try to make it a little confusing by making the original a rate. Okay, let's look at part B. Using correct units of measure, find the average rate of change of r of t from 3 to 18. So we're looking at really the average rate of change over an interval. So we're going to say r of 3 minus r of 18 over 3 minus 18. That's going to be 10.4 minus 10.7 over negative 6. So we're getting about 0.05. And that's our rate of change, and that's going to be in gallons per hour squared. And again, they're sort of messing with you a little bit here because the original thing is a rate, gallons per hour, and so it's gallons per hour per hour. We can just look at the units. That's what you really have to pay attention to, right? We've got gallons per hour divided by hours. That's what we do when we're doing a rate of change, right? It's the units of y, change in y over change in x. So if we have gallons per hour, we've got gallons per hour can be written as gallons over hours, and then per hour over hour. So if we simplify that, it's going to be gallons over hours times 1 over hours. So we got gallons per hour squared. So they're just kind of messing with you a little bit here on part B. In this whole problem by making the original thing a rate. So now they want to know, is there some time somewhere on this interval where the derivative has to equal 0? So that's Rolle's theorem, right? We want to find, so we're going to scan our table, and we know that if the height is ever the same at 2 endpoints, somewhere on that interval, our derivative would be equal to 0. So I'm looking for some endpoints that could be the same. So it looks like actually the first and last value, they have the same y value. So that means their average rate of change over that interval is going to be 0. So then the instantaneous rate of change has to be 0 somewhere on the interval. So we can say since r of t is differentiable. Remember, we have to state that. Then it is also continuous, because differentiability implies continuity. Since r of 0 equals r of 24, and we saw that both of those y values were 9.6, then Rolle's theorem, we have all three conditions met. Differentiable, continuous, and the endpoints have the same height. So then Rolle's theorem will guarantee a value of t on that given interval from t to 24, and not the endpoints, not one of the endpoints, such that, so it's that open interval, the derivative, or the rate of change of r, will be equal to 0. All right, let's look at another problem here. So you can pause the video here and take a second and read the question stem and read part A. So do that. Okay, welcome back. So is there a guaranteed value on the interval so that the average rate of change of cost is equal to the instantaneous rate of change? So what they're really asking about here is the mean value theorem. Right? Is the mean value theorem applicable? Because they're asking you, is there a guaranteed value? Does it exist? So mean value theorem would guarantee that. So we have to make sure it's applicable. So they're asking about the closed interval from 0 to 3. And if I look at this function, I notice a couple denominators here. So the function's undefined at x equals 0 and also x equals negative 3. So 0 actually happens to be on this interval because it's equal to. So the mean value theorem is not going to guarantee that such a value on the interval exists that the derivative is equal to the average rate of change. The instantaneous rate of change is equal to average rate of change. So we're going to say, since c of 0 is undefined, then c of x is not continuous on the closed interval 0 to 3. Hence, we like the hence, the mean value theorem does not guarantee a value of r on the interval 0 to 3 such that the derivative at r is equal to the average rate of change. I don't have to do it out because the theorem doesn't apply. Okay, so let's look at part B. Okay, so now they're changing the interval from 3 to 6 inclusive. So now our theorems should work because the only discontinuities on this graph were at 0 and negative 3, and neither of those are on this interval. So let's see what they're asking. Now they're saying, is there an r on the interval such that the derivative equals 0? So now they're asking if Rolle's theorem applies. So that means that our endpoints, like our c of 3 and our c of 6, should be equal. If they're equal heights, right, then that means their average rate of change is 0. So then there must be an instantaneous rate of change of 0 somewhere on the interval. So we are saying that let's start writing out our solution here. So since c of x is only discontinuity, so we'll say discontinuous at x equals 0 and x equals negative 3, then c of x is continuous on the closed interval 3 to 6 and is differentiable on the open interval 3 to 6. Now we want to show that c of 3 equals, so if I plug 3 into the function, I'm not going to waste time doing this. I already did that. I got, this is a calculator active question just because of the nature of the function. This would be on a calculator section. So you could pause the video, plug in 3 and see what you get. I'm getting 8,333.333. Remember, we round to 3 decimal places. And when I plug in 6, I get that same value. So they do have the same height, which means their average rate of change will be 0. So really, mean value theorem says there has to be a point on there where it's 0. But we know Rolle's theorem is the specific case where it's actually 0 that works. So we're going to say, so Rolle's theorem guarantees a value of r such that c prime of r equals 0. And now they want us to find that value. So again, I'm going to say that you can do this calculator active question. So if I say 0 equals that function, I put this function in y1, and then I'll put 0 in y2, do intersect, and find where those are. So we'll say that value of r on, let's see, where was I? Part B. So that value came out to be, let me say it this way. So that value of r is going to occur .098 is what I'm getting. And it's not when the original equals 0. We have to put in the original function into our calculator. In y1 and y2, we want to graph the derivative, so we're going to do that n derive, and we're going to evaluate it at x equals x. That'll be y2 is the derivative, and we want to graph not y1 but y2, and then y3 would be 0, and we want to find where those intersect because we're finding where the derivative equals 0. Let's move on to part C. On the interval, the closed interval from 3 to 9, what's the greatest cost for order in transportation? So for this one, they're talking about what's the greatest. They're talking about an extreme value. So this is going to be an extreme value theorem. So we're going to say that the extreme value theorem guarantees the greatest cost for order in transportation will happen when we're going to check our endpoints 3 and 9 and any places that our derivative equals 0 on that interval. Let's start writing some of this out. So the extreme value theorem guarantees the greatest cost for orders and shipping or transportation, for order and transportation and we should probably talk about remember, for the extreme value theorem, we have to mention that it's continuous on the interval. So on this interval 3 to 9, the function is continuous because our only discontinuities I believe were 0 and -3, so we should mention that as well. For order and transportation will occur at the endpoints. So I'll say will be when x equals 3, x equals 9, the endpoints, and any possible relative extrema. So when I look at the graph of the derivative, again, you're going to graph the original y1. You should have had the graph of the derivative in y2. When you graph that y2, you're looking for any spots on the interval from 3 to 9 where the derivative is 0 or undefined. So it's going to be at 0. That's going to be the one at 0 is going to be at 4.098, and that's the only one where your derivative is 0. So we know that the maximum is going to occur at one of those 3 spots. So we just plug all of them in. We plug in 3 to the original, we plug in 9 to the original, and we plug in 4.098 to the original. So when we do that, we should get 8,333.33. So we're doing dollars and cents here, so it's 33 cents, right? 9 will be 8,611.11 cents, and then the relative extrema one will be 8,213.67 cents. So they want to know what's the greatest cost. So the greatest cost, we know it has to occur at one of these 3 points. They don't want to know where it occurs. They just want to know what is the greatest cost. So it's that one, 8,600. So we have to kind of mention on the interval. For the interval 3, x is in between 3 and 9 inclusive. The greatest cost will occur at 9, and it is $8,611.11. All right, let's look at our last one here. I think that's our last one, yep. All right, so you can pause the video here and read the question stem. Part A, they want us to find the value of s prime of 2.5. We're going to say this is a calculator active question again because of the nature of the function. So we're going to put this function into y1, and then we'll put the derivative into y2 for n-derive. We could also go to our home screen and n-derive at 2.5 and get this value for the function y1. So you really need to do that to make sure you know how to use your calculator. I'm not going to spend time on the video going through how to do that again. So when you do that on your calculator, you want to pause and get ahead of me here. You should get 133.333. And what that means is after 2.5 months, the cars are being sold at a rate of 133 cars per month. You can't sell the third of a car, so we'll just call it 133 cars per month. Okay, let's look at B. Find the average rate of change of cars sold over the first 12 months. Indicate correct units of measure and explain what this value represents in context of the problem. So our average rate of change is going to be S of 0 minus S of 12 over 0 minus 12. That represents over the first 12 months. 96.429. And we're going to say that during the first 12 months, an average of 96 cars are sold per month. Again, I'm not wasting time calculating this number. You can go plug in your calculator, the S of 0, the S of 12, do all the work out. So part C is our last part. Is it possible that a value of C on the closed interval 0 to 12, so that first 12 months exists, such that the derivative or the instantaneous rate of change at some value C is equal to the average rate of change? So they're asking here really about the mean value theorem. So first of all, we got to make sure the function is continuous and differentiable. So the only spot where it's not continuous, therefore not differentiable as well, is at t equals -2. And that is not on this interval 0 to 12. So we're going to say that the only value at which S of t is discontinuous is at t equals -2, which is not on the closed interval 0 to 12. And so the function is, we know that this function, by the way, is continuous and differentiable everywhere because it's a rational function except at -2. So we're going to say, so the function is, continuous on 0 to 12 and differentiable on the open interval 0 to 12. So the mean value theorem is applicable. So they were saying, is it possible that blah, 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 blah. So we just answered the first part of the question. Yes, it's possible. And now, if that value exists, find the value. So now we're going to do the second part. So we've got our function. Let's just recopy it down here. It's 1500. What was it? Sorry. yeah, I'm going to multiply out the 300 to both distribute that. We got 1500 minus 2700 over t plus 2. So now let's see if I rewrite this so I can make it better for a derivative. I'll say minus 2700 times t plus 2 to the negative 1. We can take our derivative, and I get the negative 1 comes down to give me 2700 times t plus 2 to the negative 2 times 1 by chain rule. So my derivative is 2700 over t plus 2 squared. So now we can do our average rate of change over the interval from, what was it, 0 to 12. So I'm going to do the average rate of change, which is the slope of the secant line. So I'm going to do s of 0 minus s of 12 over 0 minus 12. That's going to be equal to 96.429. You should confirm that number. Pause the video, do that out. And the instantaneous rate of change at c would be 2700 over c plus 2 squared. So I'm going to show the c value where that occurs. So I want to know at what particular c value is the instantaneous, or the slope of the tangent, equal to the slope of the secant. Or the average rate of change. So instantaneous rate of change versus average rate of change. So if I multiply both sides, I get 2700 equals c plus 2 squared times 96.429. I'll divide both sides by that 96.429. So I'm going to get 28. Let me finish this one off, darn it. Let me see here. 2700 divided by 96.429. Yeah, so I get 28 equals c plus 2 squared. Square root both sides. I get c plus 2 equals the square root of 28. This was a calculator active question, so we can kind of stop doing all this, but you could have, found the intersection between these two functions there. But essentially you get plus or minus we get c plus 2. Might as well finish this out. So c equals, if I get plus or minus the square root of 28 is 5.2. So c plus 2 equals plus or minus 5.292. I subtract 2. I'm going to throw out the negative because we're on the interval from 0 to 12. So 5 minus the 2, I'm going to get 3.292. That's the c value.